Hi, my name is Brian Caffo, and I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. This is the Generalized Linear Models class of the Regression Models class. This course is taught with my co-instructors, Jeff Leake and Roger Pang. Like I said, we're all in the Department of Biostatistics at the Bloomberg School of Public Health. Okay, so linear models, to me, other people might dispute this, but to me, are the single most useful applied statistical technique. But it's not like they're limitation-free. So a couple of limitations that come to my mind. First of all, additive response models don't make much sense if the response is discrete. If it's 0, 1, then it doesn't make as much sense, or even if they're strictly positive. Additive error models often don't make sense. For example, if the outcome has to be positive, and the error is both positive or negative, you add the error and you could possibly get negative responses from the model when the observed data can never be negative. You can do things like transformations, but often transformations are hard to interpret. I think there's an actual value to modeling the data on the scale that it was collected, or the scale that's of interest. And then, particularly interpretable transformations, natural log being the most obvious one, isn't applicable to negative or 0 values. And you can get around that, of course, but you're then no longer have natural log. You have natural log of some function of the data. So GLMs are generalized linear models. They're introduced in a 1972 RSSB paper by Nelder and Wedderburn. And the GLM involves 3 components. There's a so-called exponential family model for the response, a systematic component via a linear predictor, and then a link function that connects the means of the response to the linear predictor. And we'll go through all 3 parts, but now you know what a GLM is in terms of its definition. It has to have those 3 things, but we'll go through the specifics of what they are. Let's go to the simplest example of a GLM, which is just rehashing the linear model, which is of course an example of a GLM, but as are other things. So assume that the data are normal, and that yi is the means. I'm going to use the specific notation that expected value yi is mu I, and then our variance right there, and they're going to be independent. And it turns out that the Gaussian distribution is an exponential family distribution. So I'm going to define the linear predictor to be this. The linear predictor is always going to be that. It's going to be the kind of systematic component that relates the sort of I parameters. It reduces it down to p parameters via the covariates, the x's. Okay? So that's the linear predictor. And in our case, we have this link function, g of mu, that's g of mu equal to eta. And so this is always the case. The link function is such that it links the mean of the y's to the linear predictor. That's why it's called the linear the link function. And in the linear models, g of mu is just mu, so that mu I and eta I are the same. So in other words, the mean satisfies this relationship, and then we're just back at the ordinary linear model that we all know and love. So this yields the same kind of likelihood as our just ordinary additive Gaussian linear model. Okay, let's do so-called logistic regression. Assume that our outcome is Bernoulli with success probability mu I, so that in this case expected value yi equals mu I, and 0 has to be less than or equal to our mu values, which have to be less than or equal to 1. I'm going to define my linear predictor right now as eta. So linear predictor meaning it looks just like the regression model. It looks just like our regression model, though it's not added to the. It's not the response isn't it plus error. So this function here, g of mu, in this case, is the function that links the mean of the y's, mu, to the linear predictor eta. And in logistic regression, that function is the log odds, log of mu over 1 minus mu. So just to remind everyone, hopefully everyone's had the inference class so that they can see, or they can recall that the if you take a probability and you divide it by 1 minus the probability, that's called the odds. And so in this case, the logit is the logit is equal to the log of the odds. It's a particularly nice function. We can invert the logit, the kind of so-called inverse logit. If eta is equal to log mu over 1 minus mu, if we invert it, here I added the I. If we invert it, we get this expression that mu is x above eta I over 1 plus x above eta I. So if we were to take these means and well, forget about taking the means right now. Let's just write out the likelihood for all of the mu's, right? And so this is just you remember the Bernoulli likelihood is mu I to the yi 1 minus mu I to the 1 minus yi. And I think maybe you remember it probably more as something like we did pi to the yi 1 minus pi to the 1 minus yi, but we've just relabeled p as mu. Okay, so and then we take a product in front of it because that you know, there are a bunch of independent observations and the likelihood takes the product. Okay. Okay, so if we take this likelihood and then plug in this expression into it, and then this is the expression for 1 minus mu I, then you can reduce it down to this, that the likelihood looks something like that. And fitting this, obtaining, you know, and then we could further plug in for the eta i's, we could further plug in the linear, the summation of the xi times beta. We do that here and there, and then you see the likelihood that gets maximized in order to fit a GLM. It's no more complicated than that. Let's do a Poisson example. So now our y's are Poisson mu I, so that expected value of y is mu I, and that's not true. I'll get rid of that in the slides. Where mu I has to be greater than or equal to 0 in the Poisson case, but it's unbounded on the upper side. The linear predictor is that guy, right? And the link function, let's say in this case, is log mu. Okay, and then remember that e to the x is the inverse of log x. So if eta I equals log mu I, then we can turn around and invert it and write it that mu I equals e to the eta I. So if we write out the Poisson log likelihood and simply plug in for our mu's, plug in e to the eta I, and then we wind up with an expression that looks something like this. Okay, it's interesting to note that in each of these cases, the likelihood only depended on summation yi eta I, which you can do the arithmetic and see that it works out to be this, so that the likelihood only depends on that guy right there, right? The betas we don't know, but of the data that we know, it only depends on those guys right there. So we don't actually need the full data, we only need those things. And this is simplification is a sort of consequence of the link functions that we've chosen. If we didn't choose those link functions, that wouldn't be the case. And then this has to be derived. If we want to optimize these equations, if we want to maximize the likelihood, the maximum of the likelihood is achieved at the so-called root of the normal equations, which is nothing other than the solution to this equation right here. And the WI's have have a definition. They're related to the derivative of the inverse. They're exactly the derivative of the inverse of the link function. But it has a kind of least squaresy looking criteria where recall we had to to optimize the least squares, there was this kind of product term that we had to prove was 0, and then if we did that, then we knew we had the least squares estimate. And so this is very similar, and these are, at any rate, these are called the normal equations. So I have them rewritten right here, just to remind us again. For the linear model, the variance of y is just sigma squared is constant. For the Bernoulli case, the variance of y is mu I times 1 minus mu I. So the parameters that we're interested in occur in the numerator and the denominator. And for the Poisson case, remember variance of yi is mu I. And also remember mu I itself is G inverse. It's a function of the linear predictor. So there isn't one parameter per subject, right? It involves the x's and the betas. So this equation is a little bit misleading because it suggests that you solve for the mu i's. You don't actually solve for the mu i's. You solve for the betas, but I'm using the mu's as the shorthand for the means of the y's right now. And this has to be solved numerically. You won't have to do this. The function GLM and R just does this for you. I just thought you'd be interested in understanding what the function GLM is doing. Now notice one thing that's maybe a problem for the Bernoulli case and for the Poisson case is there's a relationship. The mean of the y's in the Bernoulli case is mu I, and the variance of the y's is mu I times 1 minus mu I. But if your data, you can. This is something that's kind of testable, right? You can look at that in your data and see, if you have a bunch of binomial random variables, you can check if you have enough repeated observations whether or not that appears to hold. The same thing with the Poisson. If you have a bunch of Poisson counts, you can check whether the mean of the Poisson counts is equal to the variance. And it's often the case that you need a little bit more flexible of a variance. So what people will do is they'll take these normal equations, and instead of solving them, they'll throw this extra little parameter in there, phi. Right there and right there, and it just allows it. So it's sort of thinking of the variance as being having an extra parameter. Now this parameter doesn't depend on I, so it's just one extra parameter, not an extra parameter per subject. And that guy can help for variance relationships that are more complicated than the sort of severe restrictions put on by the assumption that the data are binomial. This should really be binomial. You don't have much to check this in the Bernoulli case, in the binomial case. In the binomial case, you do. In the Poisson case, you can check it usually if you have repeat Poisson observations. So if there's evidence that there is so-called that this variance relationship doesn't hold up, then you can do these things, but they don't actually any more longer. They don't actually correspond to the normal equations of a specific likelihood. So to give them a name, they call them quasi-likelihood, right? So these are the normal equations for quasi-likelihood. So if in R, if you say family equals quasi-Poisson, or family equals quasi-binomial, the whole point is to relax this very strict assumptions relating the means and the variances in those two models, and it simply fits the standard normal equations, but throws an extra parameter down there in the denominator. And as you can imagine, because academics like to do these sorts of things, they've proved everything about the quasi-likelihood equations, and they have, they inherit most of the same properties that GLMs do. They just don't happen to correspond to a specific model. These normal equations have to be solved iteratively. You can't write out a solution except in special cases like when the link function is an identity, and you have the linear model. So that, but nonetheless, you wind up with beta k hat and phi hat if you include this over dispersion parameter. And then your linear predicted responses can be predicted on the linear predictor space as this guy, where we just plug in our beta hats. So for example, if we want to predict the logit probability of success, then we would put that in there. And then if we want to predict the probability of success from a Bernoulli GLM, we would have to invert these predictions and get the mu hats. Our coefficients are interpreted on the link function scale. So it's sort of g of the expected value of a difference in a 1 unit increase in a particular coefficient. All the other coefficients held constant yields beta k. But notice it's done on the link function scale, and we'll go through some examples in the next lecture. It's done on the link function scale, and it's again a 1 unit increase holding everything else constant. For the iterative solving, it's variations of Newton-Raphson. For inference, it's almost all asymptotics, with some exceptions, but that we won't cover in this class. And then many of the ideas from linear models can just be brought over to GLMs. So if you have a good understanding of linear models, that will help you a lot with understanding GLMs. Okay, and then in the next lecture, we'll start going through some examples.